Next we have exercise 15. Let us consider the set X. It consists of all sequences an of real numbers for which the series of the absolute values of the terms of the sequence is convergent, and such sequences have been called absolutely convergent sequences. This is just a name, I think, only for this exercise. And on the set X we are defining two distance functions which have been tentatively called metrics. I mean, we have to show that they are metrics, and those two functions are these, dl1 and dl infinity. These names have been deliberately chosen because we have seen similar metrics on Rn. So let's now see their definitions. The dl1 distance between the sequences an and bn is the sum of this series, summation mod an minus bn as n goes from 0 to infinity. And the dl infinity distance between those two sequences is the supremum of all such terms, mod an minus bn as n goes from 0 to infinity, or the same thing, n varies over the set of natural numbers. We have to show that dl1 and dl infinity are both metrics on X. Note that these two distance functions are not exactly what we already saw in Rn, because the set is now different and the objects on which we are applying these functions are also different. Previously, the objects were elements of Rn, that is vectors with n components, but you can think of these sequences as vectors with infinitely many components. This is actually not the entire exercise, there is something else also, but let us first show that these two are metrics. So we start the solution by considering any two sequences in X. Sequences in X does not mean sequences of elements of X, objects in X, okay, which themselves are sequences of real numbers, an and bn. What does that mean? It means that the two series, summation mod an and summation mod bn, are both convergent. Note that these two series are series of non-negative real numbers, because mod an can never be negative. For no real number an can mod an be negative. So now you recall a result about such series, about the convergence of such series. Such series are convergent if and only if the sequence of the partial sums of any such series is bounded from above. And that result is proposition 7.3.1. So you go back to chapter 7, which deals with convergence of series, and by that result there exists an upper bound for the sequence of partial sums of such a series. Let that be m1 for the first series, summation mod an. So all the partial sums of that series, where this time however n won't vary from 0 to infinity, but from 0 to some natural number capital N, will be bounded from above by m1. And similarly, there exists also an upper bound for the sequence of partial sums of the second series, summation mod bn. And the partial sums are this, where n goes from 0 to n. These partial sums are bounded from above by m2. For all, okay, this is not small n, sorry. This will be capital N. For all capital N, because that's what we are varying, and when you vary capital N, you get the different partial sums. For all natural numbers, capital N. So then what you do, you consider this finite series, summation mod an minus bn, where n goes from 0 to capital N. First of all, what you can do is, you can note that this single term, only mod an minus bn for any n, is less than or equal to mod an plus mod minus bn, ordinary triangle inequality in the system of real numbers. and then in place of mod an plus mod minus bn, you can write mod an plus mod bn, because the minus is inside modulus, which will vanish. And then you can apply the sum on that sum. Summation of mod an plus mod bn is equal to summation mod an plus summation mod bn. Why? Because it's a finite series, and that's the property of finite series. So that's how you have this. I have not written those intermediate steps because otherwise I will have to write really a lot. But you know that this is less than or equal to m1 and this is less than or equal to m2. So that way we find that this finite series is less than or equal to m1 plus m2 for all, here again, capital M, for all natural numbers n. So what do we see? We see that if we have infinity here in place of n, that means if we are considering the series summation mod an minus bn where n goes from 0 to infinity, then these are the partial sums of that series, and these partial sums are bounded from above by m1 plus m2. And this is also, I mean not exactly this one, if we consider infinity here, that series also is a series of non-negative terms. So again by proposition 731, because it works both ways, that series would be convergent. That's what we are going to write next. So by proposition 731 again, this series is convergent, whose partial sum you can see here. As you change n, you get the different terms of the sequence of partial sums. So then what does that mean? It means that the dl1 distance as defined by this rule is well defined. You see, we had to do all these things because an infinite series is involved in the definition of the dl1 function. So unless you show that it is always a real number, this does not make sense. I mean, this function does not make sense. So now we do not have to bother about convergence. Convergence is always there regardless of whatever sequences an and bn you choose from X. Alright. So far we haven't said anything about the axioms for a metric space that this should or should not satisfy. Now we are going to go to those axioms. We just simply write this. Clearly axioms A, B and C are true, and these are of course the first conditions in the definition of a metric space for this dl1. But how are they true? Let us go through the details, but verbally. You will see that it's so simple that there is no real need to write things down. First of all, you consider that these two sequences are different. They are not the same sequence. Then there exists at least one value of the index n such that an and bn are not the same real number. They are different. Now you locate that term in the series which corresponds to that n, which will be mod an minus bn. Because an and bn are different, so this absolute value will be a positive real number. Now you recall that this is a series of non-negative real numbers, and you know that such a series converges to 0 if and only if all the terms of the series are equal to 0. Because that one term at least is non-zero, it is positive, so this series will have a positive sum. The sum cannot be 0. That means here we will have a positive real number. So that is one of the axioms. If the points are different, then the dl1 distance is a positive real number. So we have got one of them. But if the points are the same, then we should get 0, which is almost instantly you can see. If these two are the same sequence, then each an is equal to bn. So the series that you are looking at here, in that case, will have all of its terms equal to 0, and obviously that converges to 0. And finally, we have symmetry, axiom C, which is also obvious because this series is the same as the corresponding series where in place of mod an minus bn you have mod bn minus an. So that's why the two dl1 distances are the same. The order in which we consider the sequences does not matter. So we just have to next show that triangle inequality is also true. Then we can say that okay, dl1 is a legitimate metric on X. For the triangle inequality we need another sequence, that is another element from X. Let C and be such a sequence. Now for any natural number n, we consider this finite series, summation of mod an minus cn as n goes from 0 to n. By triangle inequality, this real number, this numerical difference is less than or equal to mod an minus bn plus bn minus cn. And then we can distribute the sum on that. I think it's better to put this within brackets so that we can understand properly that we are talking about a finite sum whose terms are this. So after you distribute the summation over this, which of course you can do using one of the properties. I am distracted today by something. This should be equality. So by one of the properties of finite series, this is equal to this. Okay. And then next what you do? Next you look at the inequality where on one side, on the left hand side you have this sum, and on the right hand side you have this plus this. So you are actually looking at two sequences of real numbers. One of them has the capital nth term equal to this left hand side. If when you change this capital N, you get different terms of that sequence. Similarly, on the right hand side also you are looking at a sequence whose capital nth term is this plus this, and the inequality tells us that the nth term of that sequence is less than or equal to the nth term of this sequence, and we know that both the sequences are convergent, which is what we proved in the first half of the solution. So by the comparison principle you can take limit on both sides of this inequality as capital N approaches infinity, and when you do so, this is what you get. Actually you don't immediately get this right hand side, there is one intermediate step also. So first what happens, I did not write those things, you can actually write limit capital N tends to infinity this is less than or equal to limit capital N tends to infinity of this entire thing, and then you can distribute the limit over this sum by one of the limit laws, and after that only you get this. You do not have to worry about the convergences of this series because we already know that they are convergent. That is because the sequences an, bn and cn all are coming from X. Alright, so we are almost there. What does this final inequality tell us? So this inequality tells us this. In fact, this is this. This is the dl1 distance between the sequences an and cn. This is the dl1 distance between an and bn, and this one is the distance between bn and cn. So that's the triangle inequality for the function dl1. That's it. That is the fourth axiom in the definition of a metric space, and that's why dl1 is a metric on X. And next we similarly show that dl infinity is also a metric on X. For the dl infinity function, we again consider the two sequences an and bn for which summation mod an and summation mod bn are convergent. Now you recall that necessary condition for convergence of any series of real numbers. If a series summation xn converges to some real number, then the sequence xn converges to 0. By that we have these limits. Limit of mod an as n approaches infinity is 0 because summation mod an is convergent, and similarly the other series is convergent, so this limit is also equal to 0. The fact that these limits are 0 is not important. What is important now is that these sequences themselves converge, and every convergent sequence is bounded. You recall that result. So these sequences are bounded. And now you consider this difference, mod an minus bn. By ordinary triangle inequality, this is less than or equal to mod an plus mod minus bn, but that minus vanishes because it is inside absolute value. So we have this for all n belonging to n. Now since these two sequences are bounded and we have this inequality and we are dealing with sequences of non-negative real numbers, that is why this sequence whose nth term is mod an minus bn is also bounded. And because it is bounded and it is a sequence of real numbers, by the least upper bound property, the supremum of this sequence is a real number. Okay, but what is this supremum? This supremum is actually nothing but the dl infinity distance between the sequences an and bn. So which is thus always a real number, and that is how the dl infinity function is well defined. Just like we have to show that dl1 is well defined, here also we have to show, and we have shown that dl infinity is well defined. Now next we go and see all the 4 axioms. In this case also, in case of this dl infinity distance also, luckily the first 3 axioms instantly they are true. Let us see how they are true. Say you consider these two sequences an and bn to be different. Again, that means for some value of the index n, an and bn will be different. Alright. So what are you looking at here? Here you are seeing the supremum of a set of real numbers, where the elements look like this, and as n varies over the set of natural numbers, you get infinitely many elements. One of those elements is a positive real number. Why? Because it corresponds to that n for which an and bn are different. What about the other elements? The other elements are all non-negative real numbers, but one of them is positive, and this supremum obviously is an upper bound for the set of all these real numbers. So it will be greater than or equal to each such real number. In particular, it will be greater than or equal to that positive element of this set also. So can the supremum then be 0? No, it has to be positive. So that way, if an and bn are different sequences, then the dl infinity value of this pair is a positive real number. So one of the axioms has been verified. But if they are the same, then all the elements in this set are equal to 0, because each an will be equal to the corresponding bn. So in that case, you are actually looking at the singleton set 0 whose supremum is also equal to 0. So in that case, you get 0 distance. Another axiom has been verified, and symmetry you can see is obvious here. That is because mod an minus bn is equal to mod bn minus an. So that leaves us with only the verification of the triangle inequality for this dl infinity. Let's do that now. So for the triangle inequality, we are going to need 3 sequences an, bn and cn. You can assume that that cn which we chose back there when dealing with the triangle inequality for dl1 is still there with us, or if you want, you can write here again. So this time for any natural number n, mod an minus cn is less than or equal to mod an minus bn plus mod bn minus cn, ordinary triangle inequality in the system of real numbers. for the absolute value function. Now this single real number is less than or equal to the supremum of all such real numbers. Obviously, because the supremum is an upper bound for the set of such mod an minus bn as n changes. Similarly, this one is less than or equal to the supremum of mod bn minus cn. You may feel that it's a bit confusing that here we are using n to mean a specific natural number. Here, however, we are using n as a variable. If you find that confusing, you can write m here, okay, then it will look much clearer. Okay, so now m plays the role of a variable and n is that specific n. Alright, but this n, in spite of being a specific n, actually is any n. It's not that it is, say, it has to be 1 or 2 or 100, not like that. Any n you take, for that n, this inequality is true. So what does that mean? If you now think of the set of all real numbers, where the elements are mod an minus cn as n varies over the set of natural numbers. For that set, all these elements are less than or equal to this plus this, which is, however, a fixed real number. So this entire thing becomes an upper bound for the set of all real numbers which look like this. Okay, so this is one upper bound, and so this upper bound will be greater than or equal to the least upper bound of that set, because the least upper bound is the least among all the upper bounds. So that means next we are going to get another inequality. So this is what we get. The supremum of such terms is less than or equal to this. But that means we have got what we want. So this inequality is just this. The dl infinity distance between an and cn, which is this, is less than or equal to the distance between an and bn plus the distance between bn and cn. And that is the triangle inequality for the function dl infinity, and that is why it's the legitimate metric on x. But there is more in this exercise. So this is the second half of the exercise. We have to show that there exists a sequence xk in x which is convergent with respect to dl infinity but not with respect to dl1. However, we have to also show that any sequence in x that is convergent with respect to dl1 is automatically convergent with respect to dl infinity. So let us next prove these things. So we first show that any sequence in x which converges in x to some point with respect to dl1 is also convergent to that same point with respect to dl infinity. And so we start the solution accordingly. We let x be any point in x which is a sequence, obviously, a sequence of real numbers for which the series summation mod xn is convergent. And now we are going to consider a sequence in x. Now we have to be very careful because the points in x themselves are sequences. So this is how we take a sequence in x, where carefully we have labeled the terms of this sequence using superscript, and we have to keep in mind that each xk is itself a sequence whose nth term looks like this. This is where we use superscript so that we can keep track of the entire sequence and the terms in that sequence. Okay, so this xkn means the nth term of the kth sequence, and this is true for any k in n. As you change k, you get different points in x which themselves are sequences. And what is our hypothesis? That this sequence converges to that point x with respect to dl1. Now we have to prove that the same limit is also true, but with dl infinity here. Let's see how we can do that. So next we take epsilon greater than 0. Whenever we want to see something very minutely in analysis, this is what we do. So we take epsilon greater than 0 because we have this limit. For this epsilon there exists a natural number capital N such that the dl1 distance between the term xk of this sequence and x is less than or equal to epsilon for all k greater than or equal to that stage capital N. But this dl1 distance is just this by the definition of dl1 metric, summation mod xn k minus xn. Okay, so this thing is now less than or equal to epsilon for all k greater than or equal to n. Note that this is an infinite series of non-negative real numbers which is convergent. So each individual term of the series obviously will be less than or equal to the entire sum, which is this, and the entire sum is less than or equal to epsilon. That means each individual term will be less than or equal to epsilon. And this thing is happening for all k greater than or equal to n. But now that we are writing each term, so n also varies. These inequalities are true for all n in n and all k greater than or equal to n. But then what does that imply? Say you fix k for a moment. K is greater than or equal to n, but you choose a specific k. And you think of these terms. These inequalities are true for that specific k and all n. So the supremum of this set of such real numbers, set I am saying because n is varying, will also be less than or equal to epsilon. Epsilon is an upper bound for that set, and the supremum by definition is the least upper bound. So the supremum will be less than or equal to epsilon. This supremum, however, is the dl infinity distance between xk and x. And keep in mind that this thing is happening for any such k, for all k greater than or equal to n. So what have we shown? We have shown that for any epsilon greater than 0, there exists a natural number n such that the dl infinity distance between xk and x is at most epsilon for all k greater than or equal to n. And that is why, let me write it here itself. That is why we have this. From here, you get this. So any such sequence which converges with respect to the dl1 metric automatically converges with respect to the dl infinity metric as well. And then there is that example also that we have to provide, that the converse is not always true. Let us consider this, it's raining heavily outside, okay, so there may be a little noise. Let us consider this sequence yn in x, where this time n varies from 1 to infinity. For convenience, we are choosing this starting value of the index n. And what is the sequence yn? Yn, you see, this is a sequence and its terms are themselves supposed to be sequences, right? Because each element in x, each point in x is a sequence. So this yn for a specific n is a sequence. And what is that sequence? That sequence has its first n terms equal to 1 divided by n. 1 over n, 1 over n, like that. And all the other terms are 0. For example, y1 would be 1, 0, 0 and so on. y2 would be 1 divided by 2, 1 divided by 2, and then after that zeros. Like that it goes. And let 0 denote the 0 sequence, all of whose terms are 0. You can clearly see that all these sequences yn will be in x. Why? Because each such sequence yn has only finitely many non-zero terms, all others are 0. So if you consider that series for this sequence yn, that is summation mod the terms of the sequence yn, that series has almost all of its terms equal to 0. So obviously it is convergent, and here everything is 0. So this is really a sequence in X, and this is a single element in X. And now if we consider the limit of these distances, TL infinity distance between yn and 0, then what do we get? If you calculate this dl infinity value, you will get 1 divided by n. Why? Because dl infinity, to calculate that, you have to consider the numerical differences of the corresponding terms of this sequence. All those differences, almost all of them will be equal to 0, except the first few, which will be equal to 1 divided by n. So the supremum of that set of such differences will be equal to 1 divided by n, that is this. That is equal to 0, this limit is 0. So by the definition of convergence, our sequence yn converges to the 0 sequence with respect to dl infinity, but it will not be convergent with respect to dl1. Let us next see how. To what we are claiming, suppose that yn really converges to some point L in X with respect to dl1. Okay. See, we are not trying to say simply that yn does not converge to the 0 sequence with respect to dl1. Actually, here we are trying to say that yn is not convergent at all. Alright. But what do we get from this supposition? That if you consider this specific value of epsilon 1 divided by 4, then because of this convergence there exists a positive natural number n, such that the dl1 distance between yn and L is less than or equal to 1 divided by 4 for all n greater than or equal to that n. Alright, and now next we start a calculation for which you can see the first part. 1 is equal to this sum plus this sum. It's a simple thing to see. Actually what is going on, you do see that the index of summation in both the sums are equal to I, but we do not see any I here because everything is constant. It does not really depend on I. So here you are looking at a sum where all the terms are equal to this. What is this? It will be minus 1 divided by 2n. That means it's 1 divided by 2n. How many such terms are we adding? N. So n times 1 divided by 2n is 1 divided by 2. And here also we are adding n times, n number of 1 divided by 2n. So this sum also equals 1 divided by 2. So their sum is equal to 1. Why are we considering this suddenly? Let's see. You can verify pretty easily that this thing is equal to the dl1 distance between yn and y2n. It's just a matter of calculation. It looks complicated from this side. If we take this one and try to see how it is equal to this, then it is complicated. But you just simply apply the definition of dl1 here and you calculate and you will see that you are getting this. And then we can apply the triangle inequality that we have for the metric dl1. And the intermediate term that we use is L. Okay. So the dl1 distance between yn and L plus the dl1 distance between L and y2n is greater than or equal to the dl1 distance between yn and y2n. But now you go back to this. This type of distances are less than or equal to 1 over 4 if this n is at least capital N. Here it is n, here it is 2n. So for these two distances also this inequality will be true. So this sum is less than or equal to 1 over 4 plus 1 over 4, which is equal to 1 over 2. So what did we find? 1 is less than or equal to 1 over 2, which is obviously impossible, and that is why our last supposition is wrong. The sequence yn cannot converge to any point in X with respect to DL1 metric, and that completes this solution. There is one more exercise which, however, we have to do next week only, and then this section will be over. So see you next week with that. Until then, this is me, Lucifer, from A Mathematical Book. Have a nice day.